Hey guys, Miss Riggs here. At this point, you should have completed your warm up. We're going to go through a another lecture on populations, and then you need to work on completing your web quest. So let's go ahead and get started. So last class we talked about different types of interactions with organisms within their environments. So today we're going to talk about what those groups are called and what makes them um, certain interactions within that population. So first, what is a population? So a population is a group of the same species of an organism living in the same place. So can we have a population of one organism um, living in North America and a different population living in South America? Of course, they're going to be different populations. They can still be the same species, but they're just going to be different populations because they don't interact with each other. So what are some characteristics of a population? How do populations grow? So there's four main characteristics of a population, and we're going to go through each of those characteristics individually. So there's geographic distribution, and remember you have your note outlines for this, so make sure you have those out. Population density, growth rate, and age structure. So let's go through each of these individually. So what is geographic distribution? So this might also be called the range. It's going to describe the area inhabited by a population. And these can vary in sizes. So you might have a geographic distribution for, say, a frog species just around a pond. Or you may have geographic distribution of, let's say, a whale species that would be much, much larger distribution. The next one is geographic dispersion. So this shows how individuals in a population are spaced. So there's going to be three different types of dispersions. We're going to have clumped dispersion, where we'll talk about these all individually as well, and why they're important to the species survival. We have clumped dispersion, uniform dispersion, and random dispersion. And these are just going to describe the ways in which individuals of a population are spread in an area or a particular volume. So let's go through those three. So clumped dispersion. Why do you think that individuals would survive better as a species in a clumped dispersion? Well, let's think about what kind of animals would live in a clumped dispersion. So these are going to be social animals. We can think of like penguins are going to be in a clumped dispersion because they help each other hold heat in harsh climates, and without one another, none of them would survive. What else? We can think of, say, grazing species. So maybe buffalo or deer. A lot of the grassland herbivores are going to be in clumped dispersions because it helps their species survive from predators. So these are individuals that are going to live close together in groups. It also helps with mating and access to food. The next one is uniform dispersion. So uniform dispersion allows organisms to claim their own territory. So we can think of uniform dispersion as like there's certain plant species that won't grow next to another plant species because neither one of them would get the resources that they need. So in these cases, there would be uniform dispersion where individuals are living at a specific distance apart from one another. So the last one is random dispersion, and these are individuals that are spread out randomly within an area. They might claim their territory, they might live in small groups. We can kind of think of lions as living in a random dispersion. They claim their territory, but they also have smaller groups or tribes that they associate with. So population density is another characteristic of population. And this isn't necessarily going to be what is a larger area or region for these organisms to live. It's going to be how many are in the smallest amount of space. So you can think of like if we compared the population of Texas to the population of New York City. Because Texas is so large, the density is much less than the population of New York City. So the population density is the number of individuals per unit area, and we can figure this out by measuring how crowded that area is. So, like we talked about, New York City is very dense population, whereas Texas would be not as dense because of the vastness of the region. Another characteristic was population growth. So population growth is affected by 3 different factors. So obviously the number of births are going to affect the growth of a population, the number of deaths, and number of individuals that enter or exit a population. So remember, one of our vocab words was immigration and emigration. So remember, immigration are moving in. So you can think of I as in. They're moving into an area. Emigration, think of E as exit. They're moving out of an area. Okay, so don't forget to complete your ticket out the door. Make sure that you're getting these questions from the lecture. You should have all of these questions to answer from this lecture today. Go ahead and pause this video and answer the ticket out the door questions, but we are going to continue because we did miss yesterday, so I want to keep you guys on track. So we are going to continue on to talk more about populations. So again, remember you have your note outline, so we'll be filling out your note outline as we go. So population, how do we determine what the population growth rate is going to be? So there's different resources that can determine the growth rate of a population. So population growth is based on available resources. Growth is a function of the environment. So certain species might grow exponentially, whereas other species have already hit that carrying capacity and are decreasing in growth. And we'll talk about what affects each of those things. This is directly determined by the amount of resources that are available to that species. So even in the same population, you could have a species that's thriving and a species that is declining in that population. There are 2 types of population growth that we'll talk about. One type is exponential growth, and every species generally starts out with exponential growth, but then eventually logistic growth is a more reasonable growth within a species. So exponential growth. Rarely do we have organisms that continue on to grow exponentially. Some exceptions might be if we have an invasive species. So right now we have zebra mussels that are coming into our waterways in America, and basically they're invasive, and so they don't have any natural predators in the region that they're invading. And so they have exponential growth. This has a detrimental effect on all of the other organisms in that area. Another example of exponential growth is actually humans. We don't necessarily fit in with other populations because of technology, medicine, and other factors. So we are still continuing to grow exponentially. It is starting to slow down because of other factors that we'll talk about. But these are some exceptions to the rule. So generally, organisms begin with exponential growth, but then they will kind of taper out, and we'll talk about why they taper out. So in order to grow exponentially, a population has to have an abundance of space and food. So basically they have unlimited resources within their population at that time of them growing exponentially. So this occurs when individuals in a population reproduce at a constant rate. Lack of limiting factors. And a limiting factor is something that causes the population growth to decrease. So if you can think of some limiting factors, some obvious ones might be their food resources, predation, so they might have numerous predators limiting their growth rate. disease. These are all limiting factors that we'll talk about. And this is a J-shaped curve, so you can see an exponential growth. I'm sure you've seen this in math class, but this is an exponential graph here. So when a population has unlimited resources and continues to grow, it is called its biotic potential. So its biotic potential is basically how much it can breed and produce offspring without limiting factors. A population that has reached biotic potential has reached its maximum reproductive capacity. That means it can reproduce as much as it can, or it has reproduced as much as it can until it hits a decline. So logistic growth. Logistic growth is generally how species grow. So you can see here on our graph, we have exponential growth, and then it's going to taper off. And it's not necessarily going to be a straight line. It's going to continue to kind of ebb and flow depending on other factors within the environment. But generally, it hits this line here, and we'll talk about what that line is. So logistic growth occurs when the population growth is slowing or stopping following a period of exponential growth. So this is the most realistic, as we talked about. And this is caused by resource depletion. So either it's running out of food sources, so the population is getting too high for its resources. It could be influenced by habitat, might not have as much habitat, it might have a limiting niche. All of these things can be limiting factors and cause logistic growth or slowing of exponential growth. So this line here that creates this S-curve, this is called the carrying capacity. And when it hits this line, that is the largest number of individuals that a given environment can support. So again, this line is created by maybe there's more predators in the area, or they've no longer have enough habitat to carry all of that population, or their food resources have depleted because they have too high of a number of their species. So a lot of times this S-curve will actually come up and then it will decrease until it hits that carrying capacity. So we talked about limiting factors, and some of the limiting factors that can have an effect on that carrying capacity are going to be food, predators, disease, changes in the environment, and we'll talk about the two different types of limiting factors. So a limiting factor causes a population growth to decrease in general. There's density-dependent limiting factors and density-independent limiting factors that we are going to talk about now. So density-dependent factors are exactly what it says. It depends on the population. It depends on how many species are in that population. It becomes limiting only when the population density reaches a certain level. So as it grows exponentially, once it hits that carrying capacity, then it's going to decrease. And then it's going to kind of stay along that carrying capacity line. This is best seen when a population is large and dense. It does not affect small or scattered populations. So competition is a density-dependent factor. Anything that depends on how many organisms are within a species. Predation is a density-dependent factor. Parasitism, disease, all of these depend on how many are in that species population. So competition, this is a density-dependent factor, occurs if crowded organisms compete for food, water, space, sunlight, and other essentials. So you might think sunlight is an odd factor to consider, but if we're talking about plant species, think about the rainforest and how we have different levels within the rainforest. And all of these plants are competing for sunlight. So they have based their adaptations basically on how to get more sunlight. This can occur between members of the same species or members of different species. So when we have competition, you can think of maybe think of two lions that are competing for a pride or competing for females. Again, you can go back to the rainforest and think about the how colorful different species are in the rainforest because they are competing for a mate. What are some effects of predation? So population size often is controlled by predation. So who can mate with who takes place in the predator-prey relationship, and it's the best mechanism of population control. Then we have parasitism and disease. Remember, these are all density-dependent factors. So disease is going to limit the growth of population. The denser the population is, the more likelihood that disease is going to be passed on within that population. So this is definitely a density-dependent factor. And basically, we talked about parasitism previously, and it's going to basically take food or nourishment from a host and basically harm that host because it's, or weaken that host because it's taking nutrients from that host. So density independent factors are different factors, and they affect all population regardless of size. These are usually going to be natural disasters that have no dependence on how many organisms are within a population. So examples are unusual weather, natural disasters, seasonal cycles. So there might be a drought that would affect the population regardless of how dense that population is. And human activities, regardless of how dense a population is, we definitely contribute to that population in general. Age structure. So population growth depends on how many people of different ages make up a given population. So age structure is going to be determined by how old that population is. And generally, this is a good curve here. This is a normal curve. We might have an abundance of younger individuals. And then as we get to childbearing age, it's going to start to dwindle off. And then as they get older, obviously we're going to have less of those populations. So this is population growth here. Populations with large numbers of young offspring have greater potential for rapid growth. So the more a population is shaped like this graph, the more rapid that growth rate is. This is going to be a more industrialized nation here. We have less growth rate in an industrialized nation because we have less children. Though we may have a lot of children in a population in a third world country, they aren't going to survive as easily as in a industrialized population. This is a graph showing distribution in the United States. So we actually have much less population within like a child age group than you would in a age structure of a developing nation here. Patterns of population growth. So the scientific study of human population is called demographics. This examines the characteristics of human populations and attempts to explain how these populations will change over time. So there's lots of factors, especially in the human population, that's going to determine how and why birth rates and death rates and the age structure of a population is the way it is. One of the biggest effects on the age structure of a population is actually the education of women. So the more educated women are within a demographic, the less children they actually have. And so when social structures are trying to decrease the amount of children a family has, that's often what they will go to, is making sure that the women in that population are becoming more educated. So human population growth, like we said, exponentially growing at this point. It did take a very, very long time for us to actually reach 1 billion people. And then after that, it just grew exponentially since then. What do you think happened between here and here? Well, we did have the Industrial Revolution, so we have um, much better healthcare. We have uh, much better technologies. And so people are surviving a lot longer and not dying of disease and other factors as we become a newer human population. So in the last 200 years, the human population has reached just over 6 billion. The United Nations estimates the world's population to be 12.5 billion by 2050. What effects will these numbers have on the Earth? What do you guys think? I'll leave you guys to think about that. The demographic transition. So over the past century, population growth in US, Japan, and much of Europe has slowed dramatically. So these are more industrialized nations. One hypothesis as to why these countries have slowed is their growth is the demographic transition, a dramatic change in birth and death rates. So as countries become modernized, they have more advancements in nutrition, medicine, sanitation. Their children survive at a much higher rate, and they have less children. Okay, so don't forget the ticket out the door here. I know this one was a bit longer, but we did need to catch up since we missed yesterday. So go ahead and make sure you fill this all out. Make sure you are completing your web quest, and I will talk to you guys tomorrow.